Now I want to show you a simulation of this system, which can give the same result than our calculated results we have seen here in this paper. But we can do more. We can add limitations of the power and reactions on this. So first, I just want to type in this signal block diagram. K then is 2.5. We have identified this. T is 10 seconds. We set this to 10 seconds, and I want to start simulation with a KC of 4. The power unity is kilowatt. The time unity is seconds. Okay, this can be done with my Regc program. In tool programme, you can have a copy of this, or on my personal homepage. I start this program and show you how to type in the signal block diagram. So first I make the size suitable to my video, my recording window. Second, you see the starting language is German, but with this button, with this American flag button, the the app language can be switched to English. Now I need the PI block first. The parameters of the PI block are block gain 4 and time constant 10 seconds. That are the numbers of my application. Then the PT1 block of my process is followed, 2.5. Again, time constant 10 seconds. Note that I have here two divisions placed between this, because I want to add a summing point here for later use of the signal block diagram for disturbance discussions. Furthermore, I want to hold place free for a second PT1 in our process. I want to add finally in the last step. So the next what I have to add is summing point here in the beginning. So summing point between, and then finally branches with the key W. This is the summing point. The input here is the disturbance. Now 2 blocks for the final addition, then feedback, signal, and minus sign for this block. And yeah, that's all. If I calculate step response, I have to click on this button. If you have done this, you see a new window, but in the original window now you see there are numbering in circles. So open inputs now are numbered starting with 71. If there are 2 inputs, the second input is 72. So you have to know, okay, number 71 is a reference input, number 72 is a disturbance input. Now look on my step response window. You see here the time range should be at least 10 seconds, I think. Input step amplitude for our reference step should be 50 kilometers per hour. Output of block I want to see is, of course, the speed here, that is number 2. And input should be the reference value 71. Here you can switch which step, which input should get the step function. Okay, if you have done this setting, click on Recalc, and then you see our speed output over time. This is 1 second, and you see if you draw a straight line, a tangent curve, this crosses the final value at 1 second, and after 2 seconds we have 40, say 44, after 3 seconds 47, and so on. After 5 seconds you're within 1% reaching the final value. This is the speed, and at the same time you can view the power signal. The power signal here is the output of block number 1. If I go back to switch number 1, you see now the power signal as calculated in our curves. The 0 up to 200 kilowatt step, and then a decrease down to final value of 20 kilowatt. Yeah, exactly. These curves are predicted with my simple mathematical equations. What we can do more here is I now store this curve. Yes, store this curve. I want to see now the next curve with the following change. Now I see that the PI block has not only a gain at a time, there is also here possible a limiter, and I limit now my signal, my output signal, to 100 kilowatt. So here I can type in the realistic maximum power output of my motor. To get now the new response, I have to recalculate the power signal. You see the red curve now shows the PI controller now is the maximum power a little bit longer than the blue curve has done this, and here the decrease goes to the same value. And more interesting is what happens with now with the speed. So I can now switch over to my channel 2. Here you see that now the storage is done with the power signal, and the red curve is now the new speed signal. If I want to have the speed signals in one diagram, I have to delete them and repeat the calculation without limiter. So they do this and calculate now the speed again, recalc the speed, output block 2, store this curve, and switch back to a limitation of 100 kilowatt. Say OK, and now recalculate the speed output with my limited motor power to 100 kilowatt. You see, of course, here the acceleration is less than the blue one. With a higher power, you can, of course, faster accelerate. Here you see this is a typical exponential function of the blue curve, but here you see, in this case, the controller takes much more longer to reach the final value. Yeah, if you wait 20-30 seconds, of course, then this becomes 0. But you see, after 10 seconds, I'm not driving 50 but 48. So you see, with this nonlinearity of the motor limitation, the behavior is worse than ideal. The question is, can we now do some additional steps? I show you what we can do in our simulation. We can go higher with our gain. Yeah, gain factor I have mentioned costs no money. It's just a ratio of two resistances. If I now exchange one resistor, say 100 kilo by 1 mech, then the gain factor can easily be increased by a factor of 10. Motor power still stays at 100 kilowatt maximum. And now look what happens with my speed signal. Note I have click this button, and if I click this button, the last curve is stored, internally stored, and here you see an indicator. The next color comes with green color, and you see if my gain is larger, the increase here, the acceleration is constant, done with a 100 kilowatt, and here the acceleration stops very near to my final speed of 50 kilometers per hour. But I think in real life the difference between 50 and this value here really not can be measured with the tachometer. So you see, in a simulation we can add nonlinearities and very quickly play with some variables which can easily be changed, and here you can adapt and optimize your system. Yeah, a last step in my simulation. I want to show you what happens if you increase more and more. You see, theoretically there is no limitation for this increase, but practically, if gain is higher and higher, of course then you have more and more problems with this very simple approximation of your car behavior. So it is good to check what happens if there is an additional PT1 behavior. Maybe this could be the delay of the motor. So I remove now this part of the branch and add a second PT1. The second PT1 just should work with a 100 millisecond delay, and I show you that this can cause severe problems. If I repeat now this calculation with this additional PT1, which is realistic, then you see, okay, the speed signal now has a small oscillation, but note what happens with the power signal in this situation. Yeah, the speed signal looks fine, but if I switch now to the power signal in this situation, then you see the power signal ends up in a very strong decrease to 0, and here you see furthermore you have negative power, which means the motor want to have negative power, means the car should brake. Yeah, so you get oscillations, and this can of course could be a high mechanical load for all mechanical parts in your system. If I do one step more and I increase this gain more and more, say up to 400, then you will see what happens in my situation of recalculation. Here you see, then you get a strong oscillation of the motor power signal down to a negative 100 kilowatt, means you have to brake with 100 kilowatts, then you accelerate plus 100 kilowatts, then you brake, then you accelerate. This, you see, is not that really what you want in your system. So you see a natural practical limitation for the increase of gain is your model must be more precise and more accurate, fitting to your real behavior of your system. Okay, so I switch now back to 4 to show you now the next step, the discussion of the disturbance behavior, if there is a signal. Yeah, so I think this is a good point to stop the simulation and open the next video for disturbance discussion.